Welcome to my obsession. My talk. The purpose of this talk is not to present something as solved, but to introduce you to some intriguing possibilities in this space which are largely unexplored, and to encourage you to get involved. While deep learning has gotten most of the attention lately, we're not going to limit our discussion to that. Machine learning, visualization, cloud platforms, even virtual reality all come into play. The goal is to help ourselves face the growing size and complexity of code bases and collaboration. So, deep learning, in quotes, little pun there. I will talk about the basic concepts of deep learning and neural nets and so forth, and ask some interesting questions, introduce some open problems, lots of pretty pictures and video, no math, and a slightly rambling story. But here's what not to expect. This is not a science-style talk. There's not an in-depth exploration of anything. I'm not going to get into the math. I don't have any answers. There's no definitive results. Unless we get our theory 100% right the first time, deeper insights only come from the mistakes that we make, from the failures of our experiments. If we leave those out, it cuts away the heart of the story. I'm all about stories. About me a little bit. I'm a principal consultant developer with ThoughtWorks, based in San Francisco. That means I'm old, but they still let me write code when no one is looking, mostly evenings and weekends. I've been a developer and entrepreneur for over 40 years, and still learning, just love it. I'm an evangelist for domain-driven design and event storming. This is my other obsession. That's a different talk. I'm not a data scientist. Math brain is really, really rusty. I probably don't understand statistics, but I'm really curious and intellectually fearless. What I mean by that is I'm not afraid to be wrong or to look foolish in front of those that know more. But my desire to learn is greater than my fear. If you stick your nose into things you don't understand often enough, you begin to understand. But enough about me, because it's really all about you. Software developers here today. Good, looks like over half. Data scientists, please hold your outrage until the end of the talk. Graduate students, anyone? Too bad, some great thesis topics in here. Managers and executives, welcome. The point of this research is not to replace people, it's to help people. Just want to get that out front. Venture capitalists, stealth mode, okay, fine. There weren't any. Science fiction authors, there's usually at least one. Are you sure about that? I think we're all science fiction authors. Software designs are science fiction. User stories are science fiction. Architecture, science fiction. It's all science fiction until it works. We work out the fiction over time, taxing our imaginations sometimes to the limit. But that's a good thing. Imagination is the key ingredient for innovation. The future starts with two words: what if? Many of the things we enjoy today, cell phones, iPads, airplanes, machine translation, those were all science fiction, and not that long ago. Imagine a computer you can talk to, or a machine that learns on its own. No big deal, we have one in our pocket now. 10 years ago, it was a little iffy. So why deep learning? All of these things have happened in the last 5 years. You remember the lip reading scene from 2001 where Hal's reading the astronaut's lips? It's like the machines are better at that now. The universal translator from Star Trek, Google's working on it. Science fiction then, science now-ish. It's a very active field of research, both commercial and academic. More amazing results every week. For example, archive.org seems to have 5 to 10 new deep learning papers every day. And I did a Google Scholar search last night for the key phrase deep learning, 17,000 results published this year. If that's accurate, that's 143 articles and papers every day on this topic. So it's popular. But what is it? Well, what is and isn't deep learning can be a little fuzzy. John McCarthy said, as soon as it works, no one calls it AI anymore. Arthur Samuel defined a field of machine learning as giving computers the ability to learn without being explicitly programmed. And then more recently, deep learning has refined that to the ability to learn hierarchical features without supervision. What really matters is the ability to learn complex, hierarchical, subsymbolic features without being told what they are in advance. Show a neural net or a deep learning system enough pictures of cats and non-cats, and it will figure out its own internal conception or representation of catness. And though the neural net's notion of catness may not bear any resemblance to ours. We'll come back to neural networks and deep learning in more detail later, but first, let's get the unspoken question out of the way, the one we're probably all thinking about. What's in it for me? As a software developer, what can this do for me? Not just applying big data or data science in my ecosystem, but producing results that make my job easier. People have been applying artificial intelligence to aid software development for decades. The results have not been all that useful to us. I'm not here to judge how deep your network is. I don't care. I'm more interested in what this technology can do for us as software developers. So here's the story. The story doesn't really revolve around deep learning, but a quest for knowledge, for answers, for enlightenment. It's an epic tale of science, fraught with wonder and enchantment. With deep learning, deep thinking, and beautiful visualizations. An excursion into the nature of software and what it means to understand a system. Okay, why not just skip to the good stuff? Well, if we have a hypothesis and run an experiment and it works, that's great. But we don't really learn much from that. It may validate our hypothesis to some degree, but that's about it. It's only when we're wrong that we can learn. And humans learn best through story. We retain it for much longer, and since we're searching for a useful model, every mistake we make is instructive. So for me, this started with a question, which sort of became an obsession, led to bigger problems within bigger problems, kind of like the classic tale of man falls in a hole, falls in a hole, falls in a hole, recursively. So what was the question? One day at work, a coworker asked me to take a look at a legacy system for a client and offer an opinion on what to do with it. Keep it, no maintenance was getting sky high, rewrite it, which was expensive and scary, salvage parts by refactoring, which nobody really wanted to do, or maybe replace it over time, build a new system and hope it just went away. So I said, sure, that's my job. I'm a consultant. I'll be happy to look at it. Can I see the code? Okay. Imagine this screen full of gibberish, JavaScript, is a small system, about 5,000 lines of code. This is what they gave me. 2 million lines of code. Brain overload. And that wasn't even the whole thing. Metrics were really no help. They identified some suspicious areas of the code. Why is the cyclomatic complexity over 11 million in this one function? But it didn't really tell me what I wanted to know. It didn't tell me how the system worked. It didn't tell me what it was for. What I wanted to find was the seams, the natural places in the system, the meaningful pieces, the places where I could take it apart safely and turn it into something else. I wanted to understand the system, but without spending months working with it. And by the way, if it did not stop to eat, sleep, or tweet, you could read 2 million lines of code in about 90 days. No, I wasn't going to do that. So what was I going to do? Clearly, we need some science. Now, I asked to see the code, and I still wanted to, but I want to see all of it at once, in some natural arrangement. I was sure I'd be able to see the seams and understand the architecture, if only I could see the whole thing at once. So I set about trying to visualize this monster. Now, software has no form and no substance. It's a purely intellectual construct. It's imaginary. I've never really seen it. Have you? So how do you visualize that? Before we answer that question, why visualization in the first place? Visualization takes advantage of our built-in cognitive processing. It reduces the cognitive load. We're very, very good at visual and spatial information processing. And here's a science chart to prove it. The blue area is vision in this visualization. You'll notice the blue area is much, much larger than the rest of the senses. Our eyes continuously and effortlessly process a lot of information, about 1,250 megabytes per second, according to Dr. Ware's calculations. Let's take advantage of that to reduce our cognitive load. Now, we can only keep so much in our heads at once, so much in our short-term memory, about 7 to 10 concepts, so we've been told. We've also been told we have different channels and capacities, one primarily visual, the other for language. That's why it's hard to read when someone is talking to you, because they're both using a language channel. Now, the 7 to 10 things rule kind of became a layering rule for diagrams. Don't have too many boxes on one page, and separate complex diagrams into layers and so on. A visualization is not a diagram. It should make sense at a glance, just glancing at it. Like this. Do you see the forest, or the trees, or both? Is this picture confusing in any way? Is your brain overloaded by thousands of trees and millions of leaves? Should I draw a box around 7 to 10 of them maybe and move the other trees to a different layer? There. Is that better? No. We don't want to reduce the detail. We don't want to squint at our systems through a keyhole. We want to increase our ability to understand rapidly. Now, this is a test. How about this one? Is this one confusing? No. Different angle, still a forest. Okay, and this probably won't be confusing at all if you live in Denver. Different angle, covered in snow, still a forest. So let's assume that our brains like complex visual stimulation and get back to the problem of finding a useful visualization. What does software look like? Maybe it looks like this. This is a program called Code City. Classes are buildings. Packages are the districts of the city. And the visible properties, the height of the building and the colors and so on, may vary by chosen metrics. You can pick any metric you want out of Sonar Cube and map it onto this. This is a pure view of the declared structure, the packages and files and classes. But it is a useful metaphor for navigation. But staring at metrics and staring at the package structure really doesn't tell us what the software does. And that's what we want to know. So I had a dream. And in the dream, was walking through a wild forest of software, and I stepped on a hello world, and I woke up wondering if it would hurt. Would it be like stepping on a Lego? What would it look like in its natural state? Well, how about a graph? The atomic reduction of a software system is a graph. Somewhere to start. Force graph layouts are really easy to do. All we need is a parser to populate a graph database. It's no big deal. So I started with JavaScript and the D3 library. Force graphs are very easy to generate in D3, but they kind of bogged down past a few thousand nodes and links. Fortunately, I found Andrei Kashka's all npm viz project, which I modified for my data. It uses the 3JS 3D library, which runs in the graphics card from the web browser, and it was able to handle, barely, the entire system. Would you like to see it? Sorry, not yet. We have to start with Hello World. It's a law. So, this is Hello World. That's the class. That's the main method. And this diamond-shaped thing is the print line call. Not obviously intuitive, is this? Not at the first glance, or at the second glance, but I do think it would hurt if you stepped on it, so we've at least answered one question. Okay, here's the entire system. Space, the final frontier. Mr. Spock, what is that? It's a giant celestial hairball, Captain. Shields up, evasive maneuvers. What a surprise. The legacy system is a giant ball of mud. Who knew? Who knew? Maybe if we just looked at one sub-project. So here's 200,000 lines of code instead of 2 million. Turns out sub-projects were just smaller balls of mud, which also should not have been a surprise. Now, one of the really interesting things about this kind of work, and by really interesting, I mean frustrating, it's difficult to distinguish a profound insight from a bug or a bad model. In this case, it's a bad model. This includes every dependency, including several 100,000 dependencies on string and integer. No wonder everything was coming out as a ball of mud. The whole graph is fully connected down to the level of primitives. Might be too much detail, you think? Maybe if we went back to the full system but only looked at, say, inheritance. Floating puffballs and one dumbbell. This actually provides a small insight. There's no deep inheritance hierarchies anywhere in this system. The deepest one is 3, and that's the dumbbell. Most of them are 2. Interesting. Not quite the level of insight we're looking for, but it is encouraging that we could tell something useful about the system just by glancing at it. Maybe if we just looked at the declarative structure, the packages and files and classes and namespace and methods and fields and so on. It should be a really clean hierarchy, right? Not so much. This is just one subsystem. It's kind of a mess. Or maybe this is just what a hierarchy looks like in a force graph, because the root node's going to be on the inside and everything cascading around it. It lays it out in a sphere, basically. Maybe we'll have better luck with the call graph. So, same subsystem, just the calls. Crystalline space entity from Star Trek Next Generation. It's kind of pretty, but I don't know what it is. Exactly, but I don't know yet. I don't know yet. I kind of like it, though. I mean, it's got kind of a spiky organic feel to it, but it's dangerous. You wouldn't want to swallow it, that's for sure. But the call links are oriented randomly, and the distance between the nodes doesn't mean anything. A force graph layout runs a physics simulation. Links are treated as springs, and they pull nodes together, and nodes are treated as things that repel each other, so they float apart left to their own devices. The simulation just pushes the nodes around in the space until the total energy is minimized. A minimal energy structure is arguably natural, which is one reason I like this. But in this particular arrangement, it's really difficult to see any kind of meaningful control flow patterns. We could label everything, but then it's a diagram. If we have to label everything, the visualization has failed. A good visualization reveals useful information at a glance. So take a glance at this picture of a tree. Do you see the tiger? Did you have to scan the picture from left to right and top to bottom and draw an outline and figure out, oh, look, a tiger? No, it's immediate. So clearly these code in space visualization things aren't working. I not only don't see the seams, I have no idea what I'm looking at. It's just not enough context. A lot of stuff on the screen, but the spatial arrangement of it is meaningless. I don't give up very easily, though. One more try, this time in virtual reality. Okay, everything really is cooler in VR. Compare seeing a picture or a video of a forest to the last time you were in a forest, and that's the difference. The experience of being surrounded by the code is kind of breathtaking. I've walked around in my code. And it didn't take long for me to effortlessly remember that there's a big clump behind me and off to my left and several smaller clusters below my feet. And I started to see some patterns in the control flow thanks to the animation. The presence and the spatial memory added another dimension. I feel strongly that this is important, that VR will help. But the visualization itself still doesn't work because the space is meaningless. So what to do? Well, the problem's larger than I thought. So this is where I sort of fell sideways into machine learning. I've been reading about it in my spare time, trying to sift through the big data, and then it was data science, and then it was machine learning, and then it was deep learning, and next year it'll be something else. And I ran across latent semantic indexing, whatever that means. And I thought maybe that'll help. So, research time. About then, Google released Word2Vec. Word2Vec is a recurrent neural network trained to predict the next word in a sliding window. You feed it lots and lots of text, and it eventually ends up with a numerical representation for each word. And this representation captures aspects of the meaning of the word and the relations between words in very, very interesting ways. The representation is called a word vector. But I guess first we should talk about neural networks. Kind of looks like a force graph. Neural network has an input layer, one or more middle layers, and an output layers. Middle layers are called hidden layers. Each element in a layer computes some simple differentiable function, some simple continuous function. And it's typically fully connected to all of the elements in their next layer, modified by a set of weights. The values from one layer are multiplied by the weights, to calculate the values that are fed to the functions in the next layer, and so on. During training, the output layers are compared to the right answer, and the difference, really the slope of the difference, the gradient of the error, is propagated backwards to adjust the weights, and that's how it learned. It's capable of learning almost any function. I sort of see this as analogous to a force-directed graph layout, except it's forces of errors pushing the nodes and links around, and a whole lot more dimensions. Word vectors tend to have 100 or 200 dimensions, not just 2 or 3. Okay. Training a neural network takes a lot of data and a lot of computational power. But since cloud computing has become as common as air, that really isn't a problem anymore. Recent advances in tools such as TensorFlow simplify the setup and take advantage of graphics coprocessors, which runs matrix calculations very, very efficiently. Training a neural network to recognize, say, images of handwritten digits can be completed in a few minutes on a standard desktop with a decent graphics card. There are several kinds of neural networks. Let's quickly look at a few to get a feel for how they work and why they're useful. That's one of my cats, by the way, Pippin. Convolution. Convolution just means that we look at a subset of the input data in a sliding window. Kind of reminds me of insect eyes. I don't know. You can use lots of sliding windows of different sizes, and they can be stacked and pooled to recognize different features, such as edges and corners and curves and so on. And then the convolved features can themselves be convolved to find higher level features, such as noses, eyes, and cats. Note that we don't tell the network what features to find. It figures that out by itself. Another interesting component is called an autoencoder. And an autoencoder is just a neural network where the desired output is exactly the same as the input. So the first half of the network learns to encode the input, generally in fewer dimensions, fewer numbers than the input. And the second half decodes it back to the output. Once these are trained, these can be used in other neural networks or other applications. One more. A recurrent neural network has many hidden layers, but they all share the same weights. This allows the neural network to learn patterns that occur in series over time. There's many more neural network patterns. I think of them as data flow components, frankly, because they all do about the same thing. Given a set of inputs and a desired output, figure out how to map between them. Many, many ways of connecting together or breaking it up. So let's go back to latent semantic indexing. Word2Vec is a form of latent semantic indexing. It uses a recurrent neural network trained to predict the next word in a sliding window. This produces a numerical vector, an array of floats, for each word. You can use these word vectors in other applications or in other neural networks. Word2Vec is not the first way to do this or the only way to do this, but it's very, very efficient. A word vector represents all meanings of a word as a coordinate in a high-dimensional space. We can treat this word vector as a direction and a magnitude, like go north 20 paces, or just as a point. The emergent structure of this space has some really interesting properties, though. For example, if you start at the position for king, the top right, and you move backwards along the vector of the word man, so you go down and to the left a little bit, you're essentially subtracting man from king. And then you move in along the vector for woman, up and to the right some, you end up at a position very near the word queen. So king minus man plus woman equals queen in this space. Similarly, if we start at mother, subtract woman and add man, we end up closest to father. What makes this interesting is these kinds of spatial relationships emerge in every language. It doesn't matter if it's English or Spanish or German or Chinese. The same relationships show up. They're not numerically identical, but they are relatively appear. It's kind of one of the ways they speed up translating from one language to another. They'll take a set of words that they know are common in both languages and calculate a regression mapping between them and use that to translate the rest of the words. In case you ever wondered how Google Translate works. That and tons of computing power. Right. There's a lot more we could say about word vectors. Probably will a little bit later, but hopefully that's enough to illustrate how useful they are. I like clean code because it cannot lie. We want to find the general topics in the source code. We want to know what the code is talking about. Is it talking about shipping or receiving or manufacturing or customers or groubles or whatever? We can only trust the code. We can't trust comments. We can't trust documentation. Documentation can be wrong. Comments can be wrong. The original authors may be dead. So in code we trust. Latent semantic indexing can help us find out what the code is talking about. What model is embedded in the code, just like it finds the concepts embedded in a web page for Google search. We can use a similar technique. Now, if we map the topics in the code into word vector space, then maybe the location will convey meaning, and the distance will imply similarity. Hopefully that provides us the basis for a meaningful space. But what would this word vector space look like? Okay, well, word vectors may have hundreds of dimensions. So we're going to have to use a technique called Dimensionality Reduction to project it into 3D or 2D space. In the following example, I used T-SNE, which I'll talk about more later. The cool thing about T-SNE is it tries to preserve local and global neighborhoods when it does the reduction. So it tends to work better than the other methods. So if we imagine our word vector space as a point cloud in 3 dimensions, it might look something like this. This is 72,000 words from a baseline vocabulary that was produced by training Word2Vec on a 3 million word sample corpus, which I think was taken from the news. Each word is 100 dimensions, reduced here to 3. One of the fun things about this space is there's a little shark-like cloud off to the left that's all the different words for money. And there's a tiny little sliver in the middle that is solely composed of words from the novel Dune. I wonder what newsfeed they were reading. Hey, as long as we're looking at words, maybe we should map some user stories into this space, because they're just words. So if you add up the vectors for the words in the story, just the title, and map it into the space, it looks something like this. Again, we're using T-SNE. Most of the stories ended up kind of in their own hemisphere with a mixed boundary. Now, in this case, I added the word vectors. I believe averaging would produce better results. But even this was useful. You may have noticed several tight clumps in there. Those are duplicate stories. There's one long string off in the fringes near the word Java that is like 200 stories about logging from different projects. Okay. How about stories and classes from one project run through the same mapping? We just uncamel-cased the class names, looked up the words, and added the vectors and mapped them in here. And it turned out pretty interesting. Most of the stories are the stories of the red dots. They're kind of at the top of a cone with the classes strewn out below them. So it's carved out a little bit of this space as its own subdomain, and I believe that's exactly what we were looking for. But what does the distance between a class and its story mean? Well, distance in this space implies similarity. So if we look at the distance between a few classes and their stories, is this good? Hard to say in isolation. But how about when the distances change over time? As the software gets revised, the stories generally won't move. They don't change, but the classes will. So what do you think it means when a class drifts away from its story in semantic space? Are we corrupting the domain model? Are we losing knowledge? Are we polluting a core class with implementation concepts? Don't know. Still doing experiments here. But I believe this demonstrates some value in the desired direction, seeing the domain in the code. Maybe we could use some of this to create, I don't know, a mind map from the code. That'd be useful. Better yet, as a domain-driven design fanatic, what about a context map? Okay, so how many ways can we think about software? We have different models for different purposes. What does it really mean to understand a system, and at what level of detail? And how much is enough to make decisions? These are all deep questions, necessitating deep learning, and yes, I like puns. So here's a list of some facets of software, and no surprise, I think the domain is the most important. Everything else is a supporting role. If you take the domain model away from the software system, the system has no purpose, only infrastructure. Domain-driven design is my other obsession, but that's a different talk. Here, all we need to know is that in this style of software development, understanding and modeling the domain is the primary driver. Domain-driven design embeds the domain model in the code via careful naming, being pedantic, but also modular structure, resulting in a system composed of what are called bounded contexts. A bounded context is both a module and a transaction boundary, focused on a single concept or capability of the underlying business domain. Each bounded context implements business-specific behaviors and contains an independent data model. If you look at the classes inside a bounded context, they're all talking about the same thing, the same way. Any given word within a bounded context has only one definition. That's part of how you identify contexts. So in theory, if we ran latent semantic indexing on bounded contexts, we'll get the topic terms that are relevant to the classes in the bounded context, the business capability topics. The dependencies between bounded contexts can be shown very concisely in a concept map. It shows upstream and downstream dependencies, also trust and sharing. Deriving this from the code would be really helpful. If I could have seen a context map of this, turned out to be an e-commerce system, it would have been much easier to make recommendations. Bounded contexts and architectural modules are both just clusters of classes, so we can map them both into the same semantic space. And that may provide a common way of viewing disparate systems. So the undercurrent here is I've just used domain-driven design to define what good software looks like. In an ideal DDD system, the clusters we find through latent semantic analysis and the classes we find inside the bounded context should be exactly the same. There should be one-to-one harmony between the domain model and the code and the words that the code uses to discuss the domain model. Thus, domain-driven design gives us a definition of what good software should look like: harmonious, mechanical, and semantic structure. Now, this is arguably an arbitrary definition. It's a hypothesis. It's intended to start a conversation, not end them. It's something interesting to measure, though, perhaps more useful than more traditional metrics. But it also gives us a way to visualize the systems more compactly as context maps in semantic space. Interestingly, it turns out we're not the first people to try to draw maps of software in a semantic space. Adrian Kunn did it first, as an Eclipse plugin. It didn't go very far, but it was very interesting. He called it software cartography. Software cartography runs latent semantic analysis on the code and the comments, and it reduces the results to 2 dimensions using a self-organizing map, which is another dimensionality reduction technique. This illustration shows the call graph that results from executing a certain menu action up in the top right corner in a graphics application. And then note the calls hop across the different code islands. The size of an island reflects the size of the classes, and nearby classes that are large enough will merge to form a single island. The location of each island is sort of indicative of some kind of conceptual continuum. I say sort of because the conceptual space here is kind of strange. Why is map value builder so far from map instance, for example? We have round rectangle 2D, and rectangle, and they're all very far apart. That kind of doesn't make sense. The idea is very good, but the resulting space seems a bit unnatural. In Kunn's user testing with developers, the developers suggested that letting them arrange the space themselves might be better. But I think the strangeness of this space is because latent semantic indexing was performed on just the source code in isolation. And this goes back to deep learning loves big data. We have big data in software development, but source code isn't it. There's almost no redundancy between the different files. So if you run latent semantic indexing on thousands of pages in Wikipedia, you're going to get thousands of articles talking about the same thing over and over and over again. A lot of reinforcement. Neural nets work best if you have 50 to 100 examples of each classification. Well, if we wanted the code to recognize what our classes were, for example, by reading a class file, there's only one example per class. And this is, I think, one of the limits of latent semantic indexing, the way it's traditionally done on source code. We have a lot of it, but there's not enough redundancy to get statistical significance out of it. Now, if we ran latent semantic indexing over lots and lots of code, we might have better results. And there's a project called Deep Code that is attempting to do that. I'm not convinced it's going to work well enough, but we'll see. So here's an end run around the problem. Instead of running latent semantic indexing on the source code, let's just synthesize word vectors for the source code instead, using pre-trained word vectors from a standard vocabulary. Now, this approach kind of fails when the word in the code is not found in the vocabulary. I currently just omit it. I could generate a random vector for it too, but so far it really hasn't mattered. The number of words that it doesn't recognize out of 2 million lines of code is a handful. Okay, now that was a lot, so let's take a step back. This is part of the data science taxonomy on worldofdatascience.com. Clearly, this is a very big space to explore. These are the landmarks and the wandering monsters encountered so far: regression, neural networks, deep learning, clustering, data visualization. Now, had I known then what I know now, this might have been a logical path, or perhaps a good science paper outline. This is what really happened. I started with visualization and it just wandered all over the place. Note that enlightenment seems further away, but it hasn't disappeared. So if all of this seems a bit overwhelming, well, it kind of is. So maybe we just ignore it. Maybe deep learning is just another fad, and it's gonna go away eventually, and it won't really change how we work. I don't think so. Here's a list of things AI is now better than humans at. All of this happened in the last 5 years. Almost all of it was due to deep learning and reinforcement learning. This kind of AI is not going away because of the beneficial feedback loop that it creates. Once you find a way to improve your product or your service or your business using AI, you have more data and more money to improve your AI. This kind of acceleration has always been true, but now it's much, much easier. We have a lot more data and way better tools and ways to apply machine intelligence. This trend is only going up. And once you implement AI successfully into an industry and into a sector, it becomes impossible to compete without it. At some point, deep learning is going to be in our face, in our industry, and in our sector as developers. This is not a fad. Tools that work with this well across multiple domains are here to stay, and they're only going to get better. Anybody remember expert systems from the 80s? Yes. Part of a prior AI hype cycle, they faded really quickly because they were hard to build, they were narrowly focused, and they're very fragile. Today's machine learning tools have none of these problems. They're going to be important drivers for progress for years. They'll eventually become ubiquitous. So let's use this to our advantage. Most of our time goes into reading code for comprehension, for debugging, 50 to 80% depending on which survey you want to believe. Trying to understand a 2 million line system in a few days is an extreme example of the reading problem, but we have the same problem all day long in smaller scales. So it only makes sense for this capability to become part of our IDE. Kun's work in software cartography was a strong first step in that direction, but we still have a long way to go. So why am I really giving this talk? Well, it's not, look at all the cool stuff I've done. Okay, well, maybe a little bit of that. It's look at all the cool stuff there is to learn. It's not going away. We're going to bump into it eventually. Let's make friends with it. It's really useful. It's really shiny. Imagine what it might do for us as developers. What if we could have a bot that makes us a Hadoop cluster capable of running this program on this database in this amount of time? You can figure that out yourself, but so can a program. Or a user interface bot that just run this command X on context Y and it generates some screens for you. Or maybe the machine could write the test for us after we write the description. Maybe we could finally have a machine to explain what a TPS report is. Or one of my personal goals would be to refactor a system from legacy to microservices. I encourage everyone to imagine impossible things and then expand the scope. Let's take a short break, step back, a deep learning breath. Made it past the midpoint. Congratulations. Think about what you do each day. What's your biggest pain? What's your biggest time sink? Feel free to shout it out. Is it users? Meetings? Reading documentation? Writing documentation? Talking to people that don't know what they want? As we continue, keep these pain points in your mind and think about how machine learning might help with them. Great. Are we ready? All right. Every time I give this talk, people ask about my toolchain. I don't really have one. I kind of have a trail of destruction. The start of this a couple of years ago was a lot more wild, wild west. The only thing available, like if you wanted to run Word2Vec, you went to the GitHub and got the C code and built it yourself. Same for T-SNE. So the toolchain was a bunch of hacked up C programs, Node.js programs, black box utilities, bits of Python, a lot of Java, things that didn't work too well or play with each other very, very well. There's still a bit of that, but the situation now is much, much better. Almost everything is available in Python and TensorFlow, and a lot of it's GPU accelerated. It even works on Windows now. You know, I have a gaming desktop computer, decent graphics card, not high-end, but decent. GPU acceleration on my Windows box sped up experiments by a factor of 10 to 20. And cloud VMs are really inexpensive. The last experiments I've been doing on a P2X8 large, 8 GPUs, 488 gig of RAM, and it makes very short work of things. You can now use the same tools that Google and Facebook use, if and when you need them. But the even better news is there are a multitude of resources for learning about this, for machine learning and deep learning and reverse engineering, visualization, statistics, and so on. Some understanding of the math behind the algorithms is helpful, but it's not necessary, especially to get started. You can use these things as black boxes and just see what they do. It can be quite entertaining, instructive, and occasionally even useful. Naturally, we're not the first explorers in this vast land. There's been quite a bit of research in applying AI to software development, far too much to cover today. Instead, here's just a few of my favorite projects. The Programmer's Apprentice was developed at MIT 30 years ago and then laid off when the author graduated. The idea was to automate the programming process using a symbolic logic called plan calculus that was capable of deriving simple programs similar to a proof generation system. The intent was to help developers. It didn't much, but the system itself was fascinating and one of the early steps in what I think is a good direction. A lot of the early work was DARPA sponsored and so on, and it really focused on applying AI to waterfall processes, including automated estimation, requirements document analysis, and project management. Don't really think that helped much either. The work itself was interesting, but it didn't do anything for the developers. And we fast forward a few decades, skipping over a lot of good foundational work in the reverse engineering field. More recently, Google has been working on predicting faults in modules. And while potentially more useful than robot project managers, this also doesn't help developers very much because it doesn't tell you what the bug is or where it is. Now, if it could find the bug and fix it for you, that would be useful. Last year, MIT's Prophet automatic bug repair system repaired 15 to 18 out of 50 test cases, depending on how long you let it run. That's 10 times better than prior methods. It was trained on bug patches from open source projects, and it seems to have learned some general pattern to characterize correct code. It takes about 12 hours to find a good solution at present. Now, this work analyzed only the interplay of variables and constants in memory. They focused on just a tiny little piece of what goes on in a program and beat the old techniques by a factor of 10. So this hints at the direction this could possibly go in. Which brings us to a headline from June. 3,000 engineers freed up at Wipro after AI learns to do their work. Now, they weren't fired, they were reassigned to do more creative work, which is the way it should be. Wipro named their system Holmes so they could compete with Watson, which I think is pretty funny. Now, Watson's off learning to be a doctor right now, but it'll eventually come back and encroach on software development. But the less grunt work we have to do, the better. There's no shortage of software that needs to be written. So here's two more, just for fun. Trained at the character level on the Linux source code, a recurrent neural network can generate nearly correct C code. Trained at the word or token level, a recurrent neural network can generate the next token in context, kind of like a higher order autocomplete. Higher order autocomplete. Never mind this fake graph. Let's learn some more cool stuff. Let's talk about clustering. If you're in a forest and someone asked you how many clumps of trees there are, how would you define a clump? Hello, nearest neighbor, perhaps by the distance between the trees. There's many ways of clustering in data science. We're going to look at two of them, k-means, just because it's really common, and dbScan, because I like it much better. K-means basically just partitions the space into k areas with a minimal average distance between the elements in the partition. You have to tell it what number k is. So generally you just run it for different values of k and take whichever one looks best. If your data looks like this, k-means doesn't work. Can't partition that space. So for something like this, we use dbScan. dbScan stands for Density-Based Clustering of Applications with Noise. And yes, I had to read that. You tell it how far away to consider something to be a neighbor and how many neighbors are required to form a cluster, and it finds clusters with maximum densities. So if you say, hey, for trees have to be no more than 3 feet apart to define a clump, that's how dbScan works. And the nice thing about dbScan is you can tell it to use cosine similarity, the angle between vectors, instead of the distance between the points, and that works much better for word vectors. There's a lot of uses for clustering. Visualization is one of them. Finding classifications in data you don't know is probably the most common use for it. It's also used for spatial and similarity analysis. If you have a bunch of interesting data, try clustering it, see what happens. If you cluster together the data points that are similar by some metric, do they map to groups in the real world in some way? This used to be called data mining, but it's a big piece of it. So what happens if we cluster word vectors from our baseline vocabulary? Now, this is the result of the best dbScan. I ran it on just 10% of the word vectors, about 7,200 word vectors. And it produced 800 outliers in this bottom layer, 800 points that had no cluster. And then it produced one cluster that had 800 points in it. And then 152 smaller clusters that had between 3 and 60 points in it. Here I'm using the z-axis as the cluster number just to separate it out a little bit. And the 2D points came from a T-SNE run. One thing to note, using Euclidean distance for word vectors in dbScan did not work at all. It found almost no clusters no matter how you tweaked it, but using cosine similarity worked very well. And it's because distance in higher dimensions is not all that relevant, but similarity of angle of a high dimensional vector is, because of the way the semantic space is structured. Now, I intended to use the centroid words from each cluster as labels, and then color code the T-SNE projection based on those clusters to give you a nice pretty picture, but I ran out of time. And you'll understand why I ran out of time in the next section. It takes time to find good hyperparameters. So you have to experiment on random subsets of your data to make quick experiments. In this case, I ran dbScan with different distances, and it gives different clusters. And here's a terrible animation of them. It looks like somebody has thumped the bottom of it. But what we're looking at is word vectors moving to different clusters, 0 to 200, based on different distance measures. Okay, dimensionality reduction. Typically, we deal with very high dimensional data. And all that means is each data point has lots and lots of attributes. Reducing that to 2 or 3 dimensions allows us to more easily see it. 3 popular techniques are T-SNE, isomaps, and principal component analysis. I'm most fond of T-SNE, so I'm only going to talk about that. T-SNE stands for T-distributed stochastic neighbor embedding. It was a technique produced by Jeffrey Hinton, and it is a nonlinear dimensionality reduction technique. It computes a probability distribution over pairs in both high dimensions and low dimensions, minimizing the divergence between the dimensions. What that means is if two things are close together, if they're nearby in high dimensional space, T-SNE tries to make sure they're nearby in low dimensional space. So it's a co-optimization process. So here's a 2D projection of some of the word vectors. Of course, you can't read any words in this. So let's zoom in. We see little clumps, months of the year, compass direction, countries, different languages down here in the corner, and so on. So let's apply some of what we learned. Now, earlier we used T-SNE to reduce 100-dimensional vectors to 2 and 3 dimensions, but we want an incremental solution. So as I find synthetic vectors from the code, I can just map them into the same space without having to run T-SNE over again. So I thought, can we generate a mapping from word vectors to the coordinates that we've already mapped using T-SNE? Data scientists, please don't spoil the ending. Here's about 72,000 words mapped to 2 dimensions by T-SNE. It's kind of a blob, isn't it? Let's look at the detail in the center. It's pretty crowded. Not really seeing any clusters or anything come out of this. This is the crowding problem. There are so many things that are close together in high dimensional space that they don't separate well in low dimensional space. This particular run could probably be improved, but any way you slice it, a 2D map of 72,000 points is going to be crowded. But you add another dimension to it, and it seems to work much better. This is the same 72,000 words in 3 dimensions. And this is basically the same point cloud we saw in the earlier animation, just drawn with the octave. Clusters of points are easier to see here. You get much better separation with the extra dimension. So, can we use a linear regression to map word vectors to these 2 or 3D coordinates that T-SNE has found? I don't know. Let's look at how linear regression works very, very briefly. Here's several data points, and we want to predict the value for the new point where x is. So linear regression imagines a line in the data space and it moves it around to find a placement that minimizes the distance to all the points. This generalizes to multiple variables and multiple dimensions and nonlinear curves. The idea is basically the same. Find an approximate line or an approximate curve. Linear regression is often sufficient for simple problems. So let's see how it works in this case. Here's the result of using linear regression to map 2D points from T-SNE, word vectors to 2D points from T-SNE. The blue points on the 0 plane are the target coordinates, and the orange points on the 1 plane are the predicted coordinates from linear regression. It looks pretty good, doesn't it? I was impressed with this. Here's the same comparison, but with 10% opacity lines drawn between the points. Note that they all sort of skew towards the center. Looks like a volcano, doesn't it? All right, maybe neural net would do better. So here's the same kind of illustration using the coordinates predicted by a neural network instead of linear regression. Note the volcano shape again. What's going on? Is this a good mapping? Well, if you look at a histogram of the distances between the actual and predicted points for linear regression, it looks like most of the points are very close to where they're supposed to be with a long tail of outliers. If we look at a histogram of the distances between actual and predicted points for a neural network regression mapping, it looks like more of the points are very close to where they're supposed to be and a much shorter tail of outliers. So at first glance, we might think that the neural network did a much better job than linear regression did. But if we look at these histograms at the same scale, there's almost no difference. Most of the points are within 0.005 units of each other, which seems very close. But unit vectors, word vectors are unit vectors. They're limited to plus and minus 1 interval. And they were originally initialized with very tiny random values. So if we go and look at the values in the word vectors themselves, most of them are minuscule, like 2.4 times 10 to the negative 12. So a distance of 0.05 is terrible. The points we're dealing with are very densely packed in a small space. So this mean distance of 0.005, that is not good. Just for fun, I trained another neural network to map the 3D coordinates from T-SNE to the 2D coordinates from T-SNE. And this gives us an even more pronounced volcano effect, minus the red lines. So in this illustration, it's a little more obvious what's happening. The predicted coordinates are all tightly clustered around the average of all of the outputs. Data scientists, you may now laugh. This is called convergence to the mean, and it means either you have a bad model or the task is impossible. There's nothing to learn. The input-output relationship is random. In this case, the model's fine. The hypothesis is wrong. There is no direct relationship between one word vector and its 2D or 3D coordinate. So why did this fail? Well, had I thought about what to expect a little bit more, I might have noticed the useless results sooner or realized what the volcano meant. The funny thing is, I knew how T-SNE worked. It works in pairs. Not on one thing, works in pairs. It actually works on a k-distributed neighborhood. So it takes like the 30 vectors around and uses that to generate the mapping. There's no way to reconstruct that taking just one word vector. I knew that. Now there's now a parametric version of T-SNE that trains a nonlinear regression model as it does the dimensionality reduction, but it's only available in MATLAB right now, so I haven't had to play with it yet. Really wanted an incremental way of adding things to T-SNE. That's not going to work. So here is a 2D projection of a subset of our word vector space. I want to know, can we get from this and create something like this from it? Some kind of stable, predictable topic map. This should give us a common space for context maps with stable spatial locations for concepts. What I mean by that is shipping is always north and accounting is always south, and they don't move around. This is a really simple made-up example of one. Now, before we pretend to project a tiny context onto it, let's consider if this is feasible, because I don't want another big fat failure here. All right, we can use dbScan to cluster the word vectors. We already know that works. We can look up centroid words for each cluster. That's a simple lookup. We can use the cluster indices to change the color coding to make the map look nice. That's pretty trivial. This is incomplete. It's ongoing because I wasted a lot of time trying to do something that wouldn't work in the first place. The outcome of this is uncertain because I don't know precisely what word clusters and thus what topics we're going to get until I run it and see. But I don't think there's any, this isn't going to work steps in this. And once you get past that, you use the same technique on the synthetic word vectors from the code and project them into the same space. The T-SNE implementation in Python can be warm started, which should give us the incremental projection that I want. But again, I ran out of time. Like last night, ran out of time. So, assuming all of that works, we might end up with something like this. What does this system do? Well, they harvest, ship, and package things, obviously. It's pretty clear. Now, we may be able to find substructures. The notion of a bounded context has no scale. It's like a cluster. You can have clusters of clusters of clusters, and context within context and context. It applies at all scales, so this might be appropriate. We can also look at our architectural modules this way. Projects and packages and so on can be related, can be treated as just sets of classes, which is a cluster, and mapped in exactly the same way. You can label them using the centroid words or using the parent package name, for example. Project them into topic space the same way we do for semantic clusters. For a given system, the difference between the semantic clusters and the mechanical modules, the architecture, might be informative. In this simple example, they're pretty close to each other. But what if they weren't? What if the mechanical and semantic clusters were very different? Can we calculate this? Can we see this kind of semantic tension? For example, half the classes related to materials in the production system yearn to live in the inventory services cluster. We can calculate a simple tension or pressure metric just by counting elements that want to leave versus elements that are happy to stay versus elements that want in. This may indicate different types of misalignment and possible refactorings. We can also calculate a more complex tension metric using vector differences between the center of the cluster where the code wants to be and its current location. Have you ever gotten anxious reading someone else's code or your own? Confused, irritated, annoyed, sometimes pleasantly surprised, but usually the other things? I think all of this is related to our expectations, to our own mental models, based on our own experience, our own culture, what we might call common sense. If the code you're reading doesn't match your expectations, it doesn't connect the dots for you, you feel uneasy. And if it does, you feel good. Both of these, I think, are related to semantic tension. High tension, high anxiety, implying a higher cognitive load on the developer. Can we use this? Can we let the semantic tension tear apart the mechanical structures? And if so, would it come apart at the natural seams that we started looking for? Is there a balance to be struck between semantic shearing forces and modular cohesion forces? I don't know, but it's going to be fun to find out. This gives us another way of thinking about software, potentially more interesting and may lead to more powerful tools. Oh damn, yeah, databases. Most of the focus has been on the code, but we can't ignore databases, unfortunately. However, if we extend our assumption that domain-driven design defines good, our notion of goodness, we can assume that the semantic clusters are the same as the bounded contexts. And this gives us a clear goal because each bounded context, each cluster, is also a transaction boundary. So all we have to do is find the domain transactions in the database, extract the database schema and operations necessary to support each operation within the bounded context, and then figure out how to synchronize, notify, replicate, distribute the data between bounded contexts. That's another problem. Event streams are awesome, though, just saying. There's a dark side to deep learning. It's really difficult to know what it's learned. All the features are just numbers, hundreds and hundreds of numbers. It's almost impossible to relate these back to any kind of symbols or rules that we'll understand. This carries with it a risk that the neural network is using features that are coincidental instead of fundamental. And it is very much subject to the bias in the data. One of the more famous examples of this is an early neural net experiment. The military, US military, tried to teach a neural net to tell the difference between a Soviet tank and an American tank. And it worked beautifully. So it was 100%. And then they went to test it after training with some new pictures, and it failed miserably. Because it turns out all of the pictures of Soviet tanks had been taken on a cloudy day, and all the pictures of American tanks had been taken on a sunny day. That's all it learned, cloudy versus sunny. Didn't know anything about tanks. A deep neural network trained on ImageNet may classify this image as an electric guitar. Now, if you squint at it a little bit, it sort of looks like a fretboard, but the image as a whole is clearly not a guitar. In other experiments, changing just a few pixels in an image of a lion in a way that's imperceptible to humans convinced the neural net that the lion was a library. Got an overdue book for you? No. Our image recognition capabilities evolved over millions of years in a hostile environment, a place where mistaking a lion for a library would not be made more than once. So the problem here is we need to somehow bridge the symbolic and subsymbolic gap. And there's some efforts in this area that are promising. Adversarial training is one way to do it. This includes including images in the training that are intentionally wrong to force the neural net to learn better rules. It also includes training two different models at the same time. Like you might train a neural net to recognize something and you might train a random forest to explain it at the same time. The main point is, since we don't understand how these things work or what features they latch onto, we can't assume that they work like we think we work. This makes it difficult to trust their output completely. Going back to word vectors for a moment. King minus man gives us a relative vector. That relative vector in some way reflects the relationship that's left over when you subtract the concept of man from the concept of king. The relationship we might call it royalty. But if you look at the word vector for the word royalty, it is nowhere near the difference between king and man. And that's a consequence of the way the system is trained. What is interesting to think about, though, is if we have enough examples of these kinds of relationships, gender and plurality and containment and causation and so forth, we may be able to find a consistent set of relative vectors within a word space. And if we can do that, it may allow us to just scan that word space and extract a knowledge graph from it, to turn the vector representation into a knowledge base that we know how to deal with symbols. It may also let us synthesize word vector spaces from existing knowledge graphs, both of which would be powerful. Now, there is an extraordinary size problem here in the vocabulary I'm working with, which is a tiny one, 72,000 words. The one Google works with is 3 million words. Right? But in the tiny one I'm working with, 72,000 words, would have 49 million relative vectors, requiring 2.4 times 10 to the 15th pairwise distance calculations, and my desktop's not going to be able to do that. Not in Python, anyway. This is an incomplete experiment. I think it can be done. I haven't gotten into it yet. One place I believe this would be really useful is feeding the results into other tools, such as PSI. And PSI stands for Predication-Based Semantic Indexing. What PSI does is it encodes relationships as high-dimensional vectors. You don't have to train it, you feed it. You feed it a stream of triples, subject-predicate-object pair, triples, and it encodes each relationship as vectors in a high-dimensional space. This approximates a knowledge graph using a sub-symbolic representation like a neural network. There's a vastly oversimplified explanation of how it works. It has two kinds of vectors: elemental vectors that are randomly generated, and they're constant. They never change. So each word would have an elemental vector. Then it has a semantic vector, and those are constructed. And the operations to construct a semantic vector are bundling, binding, and unbinding. In bundling, you take component vectors and you find the bundled vector that is maximally similar to both of the components. You cannot unbundle. This is kind of a one-way process. In binding and unbinding, you use a different operator to combine the components in such a way that you can unbind them later. So you can think of a semantic vector in PSI as equivalent to a node in a knowledge graph plus all of the relationships that go in and out of that node encoded into a vector in a high-dimensional space. It's a superposition of all the relationships to or from an elemental concept. What makes this cool is you query this by distance and similarity, just like in a word vector space. Our code is a mass of relationships, as are our databases and ontologies and configuration manifests and so on. So I think this is going to be a very useful technique. If we can ask it useful questions like this: if X consumes Y along path ABCD, then what consumes Z? ABCD might be inherits from has method, has argument of type. Any of the relationships we might find in our code. What makes this so powerful is a query like this. It's a four-hop query. The query gets encoded into a single vector, and we only have to scan the semantic vectors once to find the answer. So running a query in this kind of system is linear in the number of concepts, not exponential in the number of links. And with GPUs, that's going to make this way faster than traditional graph databases. It is approximate, but it's good enough. Now, I really like this approach because it takes symbolic information and it absorbs it into a sub-symbolic representation that is compatible with the way neural nets do things. It does it without any repetition or optimization, and we're able to recover our symbolic information from it. I suspect PSI might perform even better if it used pre-trained word vectors instead of random elemental vectors, or pre-trained relative vectors for the relationships. I haven't run that experiment yet either. Now, I talk about the things I've done and the things I haven't done and things I'd like to do, and you might get the idea that there's some kind of grand plan or roadmap here. Not really, no. We've gone many places together, and thanks for hanging in. There's no clear destination, but I was able to draw a little bit of a roadmap in hindsight. If there's any Phineas and Ferb fans in the audience, you'll get the innator reference. This was made while exploring the space, connecting the dots and thinking deeply about software. We parsed the code to extract a dependency graph while also mapping the words in the code into a baseline semantic space. We can use modular decomposition to extract the mechanical or architectural clusters. While at the same time, clustering just the words in the code to get the semantic clusters. Then we can calculate and visualize the overlap or the difference, or the tension between the software architecture and its latent semantic structure. This is a work in progress and probably a perpetual work in progress. So what does any of this have to do with deep learning? Well, not a whole lot. Deep learning is just a tool. It was the shiny thing that made me fall down this rabbit hole, and hopefully it was the shiny thing that got you to come to this talk, and so it worked. It's a very interesting and a very powerful shiny tool, one that I think we can use to help ourselves. Even the output of deep learning, word vectors, are tremendously useful. It's interesting to think about how to apply, say, convolution or autoencoders to source code. There's only been a little bit of work in this area. Well, some of it is impressive and slightly scary. Speaking of scary, remember this fakey graph? Is this the beginning of a trend? I don't think this is anything to worry about, do you? I mean, we still have our imaginations. Maybe. Some people believe our entire industry is shifting towards machine learning. And whether we agree with it or not, these emerging tools are extremely powerful, so it would be wise to understand them, at least a little bit, in case they are meteorites. But this is really the biggest problem. We haven't had a significant brain upgrade in 1,000,000 years, and our technology doubles every 2 years. In fakey graph form, it looks like this. Note the flat line for the brain. Our brains have limits. We must learn to use them more efficiently, to expand our limits. This may require radical new tools and approaches. So how can we increase our limits? Well, the biggest constraint would seem to be reading code. Developers spend most of their time reading code for understanding and orientation. Automating that would save a lot of time and effort, so that's something to look into. The way we interact with our code is very linear. We rely on reading text and short-term memory. We're only using one of our cognitive channels, the language channel. So what if we made the interaction more direct and in a more meaningful space? With some clever machine learning, could we automatically restructure a monolith into microservices? Maybe. How about embedding a model of the software into the software? Feed it its own analytics and Twitter sentiment and let it adapt itself. I know, science fiction, for now. But imagination and persistence overcomes limitations. The difference between an adventure and an ordeal is attitude. Choose adventure. Choosing adventure doesn't mean you're not allowed to whine about things that don't work. Every adventure has its ups and downs, surprises both good and bad. But answer the call and see where the adventure takes you. Because it's an adventure into the unknown. It's not a project. Obi-Wan, you must learn the ways of the Force, Luke, if you are to accompany me to Alderaan. Luke, I was going into Tashi Station to buy some power converters. Vader, you can waste time with your friends when the galaxy is saved. Okay, Vader didn't really say that, but you know he would. I was just looking for something to help me understand a system more quickly, maybe learn some cool stuff in the process. And then one day, I saw the Codebases infographic on informationisbeautiful.net and was stunned. Let's look at just a few points of interest. points of interest. The average iPhone app is larger than an entire small business system just 2 decades ago. When Photoshop was released in 1990, it was huge. At 100,000 lines of code, it took forever to load. Quake 3 in 99 was a hefty 300,000 lines of code. The competitors to Quake are 4 to 6 times larger in just a decade. The first useful version of Windows was a monstrous 2.2 million lines of code in 1992. Note that Photoshop 6 is 42 times the size of Photoshop 1 in only 10 years. While Windows NT is over 5 times the size of Windows 3.1 in just 4 years. Now, Linux 3.1 is larger than the software required to run a Boeing 787 jet, which makes me wonder what the jet is missing. Probably device drivers of some kind. Oh, a user interface, that's what, a decent user interface. Yet, and here's an anomaly, Windows 7 is the same size as Windows XP. It actually stayed the same size for about 8 years. Meanwhile, Facebook grew and grew. It's now over 60 million lines of code, but it pales in comparison to Google, over 2 billion lines of code and 9 million unique source files. And here I was complaining about a measly 2 million line system. So this made me wonder if software size and complexity is actually growing exponentially already. So one of the problems with exponential growth curves is that 0.01 looks a lot like 0.02, which is nearly indistinguishable from 0.04, and really close to 0.08, and so long, and by the time you realize the uptick, it sneaks up on you. And this is how it's going to sneak up on us. IoT is coming, and it's going to explode, not just the sensor code and edge computing, but integration, and the data volume is going to multiply. Another billion people are going to come online in the next decade, maybe less. Everything will eventually be connected. More people, more problems. Is massively online distributed development a thing? I think it is. We call it working remotely. It's just not very good yet. And do we really need deep learning for all of this? Well, yes, we need all kinds of learning, plus VR collaboration, meaningful visualizations, and much, much better tools. The more we automate as a foundation, the more we can build on top of it. I don't think AI is coming for our jobs anytime soon, unless our jobs are rote, and if so, good riddance. The challenges of the abundant future, though, will require more software than we can reliably build with our current approaches. So where to start? Start where you are, what you know. Explore, experiment, notice, and solve your own problems. This stuff is cool, and it gets cooler every day. It's not magic, and it's not always a breeze, but it is worthy of attention. Hunt it down and make it work for you. Notice your own routine and pain points, and imagine them gone. Ask what if a lot, especially out loud. What if we could refactor from one architecture to another? What if we could massively collaborate in a distributed virtual environment that was meaningful and effective? There's some academic work in this area that's clearly not enough. An understanding of some of the data science principles and techniques is required, but a PhD isn't. I haven't studied calculus in 30 years. I haven't used calculus in 30 years. When I said math brain was rusty, I wasn't kidding. But it didn't slow me down. Explore, break things, learn by solving your own problems. Machine learning and deep learning are shiny new tools, and that ought to be enough for any developer, really. Any questions? Yes. Wait for the mic, please.
I'm just curious what happened with the legacy system and all the JavaScript.
Oh, I did. It was actually in Java. I used more traditional approaches because I only had a few days to do it. And the answer, of course, was it depends because I'm a consultant. But I couldn't let the question go. So, yeah, I spent 3 days answering their question and then the last 2 years trying to answer it better. Yes, sir.
So, as a data scientist, I'm holding the thought at the end, right?
Thank you for not throwing anything.
So I just wanted to comment. I'll say 3 comments to keep it as short as I possibly can. The first one, you mentioned, humans have a certain things that we're good at, and machines have a certain things we're good at. So one of the things I would encourage everyone to do, visualization is a very effective tool in certain settings, and we're always limited that we can look at most 3 dimensions. Computers are incredible at looking at things in hundreds, thousands, tens of thousands, and upwards number of dimensions at one time.
Yes.
So trying to visualize what a computer sees is frequently very difficult. So knowing how to look at what the computer is computing is a challenge all by itself. The second one, as I think you've definitely gone through and described, AI is incredibly useful in many contexts, but at the same time, it will always give you an answer. No matter what question you ask it, you will always get an answer back.
That's right.
And it's very difficult to know when the answer is good or bad.
That's right.
So I'll lead that into the third and final comment. Your third bullet point there was take a data scientist to lunch.
Yes.
I would strongly encourage people here, if there's one thing you can take away from this, there is a tremendous amount of expertise in the field of statistics and data science and computer science, but they don't know what you know. You know what you know, but you don't necessarily know what they know. Have the lunch. Just having a lunch. I literally sprung on someone once as they were walking out of the bathroom. I'm like, I heard you talking about something a minute ago. They're like, looking at me funny. I strongly encourage, just take these people out, and that one conversation can go into very interesting directions.
Thank you. That wasn't a question.
Sorry. Can you talk about the difference between statistics and AI and machine learning?
Not coherently. This gentleman probably can. Take him to lunch.
So speaking of Star Trek, Star Wars, I feel like it was Empire Strikes Back. You get the cliffhanger, and I thought it was all going to be solved by the end of the presentation.
Sorry.
What were you able to drive any type of mapping that seemed to help you get a idea of this code base that you were facing?
Only in my imagination so far. I was literally trying to complete some of the mapping work last night on a cloud VM and just finally realized I should probably rehearse instead.
Okay. So was there a preferable road that you went down that you think is more promising than the other paths?
DB-scan, T-SNE with warm start, and generating a context map, I think will give me what I wanted 2 years ago. A recursive overview of the system without having to read all the code myself.
Okay, and then one final comment, which I just have to say. So in reference to the graph where you had the brain, that was constant. Yet what was interesting is that the brain is what actually came up with that graph.
Yes, it is.
Itself. So, okay.
Thank you.
Anyone else that I'm not seeing? No? Okay, thank you. I promised you it would be interesting, and it was.
2 more things.
Okay.
The first one is I should mention, again, that I'm writing a book on head-first domain-driven design for O'Reilly. Should be out end of this year, beginning of next. ThoughtWorks is hiring. And when you get into this, do little things to give yourself quick wins. Set yourself up for success. And I'll give you an example of that right now. If everyone would stand up, please. Thank you.